before I start to talk about orogenic collapse, first I want to introduce the concept, what is orogens, and then I will go to the definition of orogenic collapse. I would present you various mechanisms and conceptual models of orogenic collapse, and also some debatable mechanisms for that. Then I would present you some analytical model and show you some geological examples. And finally, I will summarize. If we think about orogens, we usually think about mountains. Whereas when we think about orogenesis, we think about mountain building. And even the word orogenes means the birth of mountains. But this is not a complete definition what the orogenes is. So orogenes is a large-scale process of crust deformation, mainly due to compressive forces at the plate boundaries, commonly accompanied by metamorphic and magmatic processes. So commonly, mountains they commonly coincide with the compressive plate boundaries. And for example, the Himalaya, they coincide with the collision that took place between Indian and Eurasian plate. But here it is important to notice that not all mountains are formed due to orogenic processes. Example of that is, for example, Hawaii. And in this case, the mountains are of volcanic origins. On the other hand, the orogenic processes not necessarily need to lead to the mountain buildings. And the example of that is accretionary prism, which formed due to orogenes, but this didn't lead to the mountain formation. So to summarize, that not all mountains form during orogenic processes, and not all orogeneses form mountains. We commonly find orogenic belts at the convergent plate boundaries. And because we distinguish three types of convergent plate boundaries, we also distinguish three types of orogens. And these are the oceanic-oceanic plate boundary, oceanic-continental, and continental-continental. Japanese islands are the example of the orogen that form at the ocean-ocean plate boundary. And the orogenesis lead to the thickening of the crust and formation of volcanic arc. The sediments of marine origins are accumulated in the accretionary wedge. The metamorphic and magmatic processes are common. The Andes are an example of oceanic continental orogen. And in this case, the orogenesis lead to the more pronounced thickening of the crust. Also, the accretionary wedge was formed, and the magmatic and metamorphic processes are observed in these regions. And finally, the continental-continental plate boundary. And this collision between two continents is usually it usually follows the ocean-continent collision. And then rocks that form in the previous stage, they are incorporated in during the continent-continent collision. In this case, we observe a significant increase of the crust. And with this type of orogenesis, the rocks are highly deformed. So orogens are very complex structures that contains rocks of various origin. We observe them sedimentary, magmatic, and metamorphic rocks. And all of these orogens, the orogenic processes, they lead to significant increase of the crust. So how do we know that orogenesis leads to the increase of the crustal thickness? So this we can observe on the surface. And here I present you the example from Himalayas. So we observe mountains on the surface, but we also observe the deep mountain roots below the surface on the seismic cross-section. And in this case, the mountains, they're elevated on the around over 8 kilometers. And the mountain roots, they reach above 80 kilometers. In this respect, we can say that orogens, or in this case orogens, they're like icebergs. There's only a small tip of iceberg that swims above the surface, that stands out above the surface. But why orogenic structures are elevated, and why do they have roots? This can be explained by the theory of isostasy, which says that the mass per unit areas of two columns of rocks that are above the certain level are equal. And here I show you examples. And this theory says that the pressure at this level, which is called the compensation level, has to be equal above all of vertical stress has to be equal in all of these cases. And the mass here is related to the height of the column and then the density. So the two columns, when one of them has a smaller density, it will be higher than the other column that has higher density. And this explains why continental crust is so elevated, because it has higher density than the swimming around mountain and then oceanic crust. And here I present you the geological map of Europe and also a topography map of Europe. And rock studies of in various places, they show the common occurrence of the orogenic structures. And here I want you to focus on these German-Polish caledonites. And we know that these rocks there, they were affected by orogenes. But when we look at the topographic map, we don't see any mountains. When we take a cross-section through these German-Polish caledonites, and here I present you the seismic section, we also, in this case, we don't observe any mountain roots. In this map, I present you the depth of Moho. And then we see that the depth of Moho is on around 30 kilometers, which is assumed to be the average, the normal, the rocks, the crust there has normal thickness. And on the other hand, when we look at the places of the active orogens, for example, Alps, we do see elevation. And we also see the depth of Moho is around 50 kilometers. So this brings the question, so what happened to the orogens? In structural geology, it is usually often described as a collapse. But here I show you the engineering definition of what collapse is. And collapse is a loss of the load carrying capacity of a component or member within a structure of the structure itself. And here I show you a few examples what I think the collapse is. But when you think about the orogens, we should I had a little bit to modify my imagination what the orogenic collapse means. It basically needs to get rid of the process that leads to erosion or the elimination of mountains and also elimination of roots. And orogenic collapse is often associated with camembert cheese is often used as an analogy for the orogenic collapse. So how that works? So when you think that you take a cheese, you leave it in a warm place. After some time, it just starts to flow and collapse. So camembert is usually used to show what the orogenic collapse means. But I found various definitions of that. And all of them, I would say they're not very intuitive. And they all refer to gravitational potential energy. And I chose one definition as an example. And you will see this definition also in further slide. So, orogenic collapse occurs when the gravitational potential energy causes the thickened and elevated zone to spread laterally under its own weight. So, in order to understand it, we have to understand what this gravitational potential energy is. Gravitational potential energy is the integrated vertical stress over the column. So here I presented two columns of rocks, and on the diagrams on the right I plot the vertical stress as a function of depth. And then the integrated vertical stress, we can imagine this is the surface below the curve. And because these two columns, they have different vertical stresses, they will also have different areas. The difference between this gravitational potential energy, this is this horizontal force that eventually leads to the lateral spreading. And this is also called gravitational force, lateral force, or the net horizontal buoyancy force. But it is not that always that when we see the existence of gravitational force that all rocks start to collapse. The gravitational force must be greater than the resistant forces and to produce this lateral flow. So, for example, if you think about the camembert cheese, if you put it in the fridge and then froze it, it will not collapse because the strength of the cheese is too high to produce the flow. And also when we put it in the box, it will not flow. So this relation between the gravitational force and the strength of the lithospheric column can be described using the Argand ratio. And this is exactly the ratio between gravitational collapse and the strength of the column. If Argand ratio is bigger than 1, then the gravitational forces will play a role into the formation. Whereas the Argand ratio is smaller than 1, the gravitational forces are negligible and the deformation will not occur. And I found in literature that sometimes many authors refer that if we have some surface uplift, it will lead to this column that is a little bit more elevated would have higher potential energy. But it's not really the case. it's not always the case. So there is some confusion between the definition of surface uplift and gravitational potential energy. And here I show you two examples. In the first one, I have two columns of rock, and they have different density structures. On the left side, I show the vertical stress as a function of depth, and for these two columns. And again, this difference between these two stresses, this is this gravitational force. And we see that in this case, in the rock that is elevated more, the flow would be from this column to this column. But in the other case, we don't have any elevation. And we have here also the different density structures. Again, in this plot, this area shows the difference between gravitational potential energy and then direction of flow. And in this case, although we don't have any difference in surface elevation, the flow would appear and be from that column towards that column. There are various models of gravitational collapse. And they are usually divided into two modes. The mode that is related with the fixed boundary collapse, and then the free boundaries. In the case of fixed boundary collapse, there are three different types distinguished. And the first type is when the deformation occurs in a brittle way in the upper crust. As the analogy, I show you the example of the landslide. And it's important to notice that this process might lead here, when you remove some rocks, it might lead to the exhumation of rocks that are below. The deformation can occur in a ductile way, and then it will occur in the lower part of the crust. And this is what I would refer to as an analogy of the camembert cheese. Well, as you know, that this type of deformation would really depend on temperature. And temperature changes can be driven by the conduction, advection, or production, heat production. So if you imagine the camembert that we leave in a cold place, on a warm place, it'll be different. So the stress, the temperature profile across the crust is very important. And then the emplacement of various magmatic bodies into the crust, or heat production due to the decay of radioactive element would play a role and would promote the gravitational collapse. We can also observe, or the model also assumes that the formation can be brittle in the upper crust or can be ductile in the lower crust. And this type of deformation can occur in a mode with a free fixed boundary collapse condition and then free boundary condition. In the context of gravitational collapse, there are other processes that are usually described in literature, and these processes contribute to the orogenic collapse. And these are delamination and slab break-off. So in the first case, we have the increased lithospheric thickness, and then this produced the instability that then eventually can lead to the detachment of the lithospheric mantle. And that promotes the uplift of the hot asthenosphere and the increase of the temperature of the lower crust, and then potentially could lead to the gravitational collapse. In the second case, when we have subduction, similar thing can occur, but in this case, that will be the break-off of the downgoing slab. And then this process would also promote the uplift of the hotter asthenosphere, warm up the crust, and then could lead to the collapse. However, there are two other processes that I found in literature. They are commonly associated with orogenic collapse, but in my opinion, they don't fit to the definition. So if we again read, the orogenic collapse occurs where the gravitational potential energy causes that the rocks start to spread under its own weight. But then we have two other processes, such as adduction and erosion. So the adduction, it occurs when we have the slab going down. We have break-off of the slab, but then the whole crust is exhumed due to the buoyancy forces. In the second case, when we have erosion, the erosion leads to the decrease of the crustal thickness. It removes the mountains from the top, and due to isostatic conditions, the rocks would uplift. If the erosion would continue, this process could lead to decrease of the thickened crust. And here it's important to say that the difference between surface uplift, rock uplift, and exhumation. So surface uplift is the change of the surface with respect to the geoid. The rock uplift would be the displacement of the rock with respect to geoid. And the exhumation would be the displacement of rock with respect to the surface. And because exhumation is commonly attributed to gravitational collapse, I can show that erosion can also lead, theoretically, to the same outcome. So here I showed a picture, and then we have a thickened crust. We have a reference point. Due to the erosion, we remove the mountains, and due to isostatic uplift, the rocks is moving up, and eventually it would end up on the surface. So erosion is also the process that can lead to the exhumation. So although these two processes, adduction and erosion, do not fit to the definition of orogenic collapse, maybe it means that we don't understand what the orogenic collapse means, really. Or maybe the definition is wrong. So, to conclude the theoretical part, the orogenic collapse depends on the thermal-mechanical evolution of orogen and mass transfer. The thermal evolution is controlled by the heat production, heat conduction, and advection. And the formation is controlled by the balance among tectonic forces, gravity forces, and buoyancy of rocks and magmas. Analytical model. Here I want to present you an analytical model that tries to find the relation or competition between gravitational collapse and erosion in the destruction, how these two processes play a role in the destruction of orogen. And in this model, there are various assumptions, and the model is very simplified. The topography is isostatically compensated. There are only linear viscous materials used for both the crust and the mantle. The thin viscous sheet model is used for the gravitational collapse, and the fusion model for erosion. In this model, the crustal thickness is given by such a form. The isostatically compensated topography would be given by such a form. And first, only erosion is described. The rate of erosion is given by such a formula, where K is the transport coefficient, and it is proportional to the slope of the surface. And the crustal thickness, the evolution of crustal thickness, is described by such a relation, where tau E, this is a characteristic time for the erosion. So what does it mean? It means that the crustal thickness at the characteristic time, this characteristic time, in comparison to the initial crustal thickness, would be like 1 to the exponent, which, for example, would mean that initially, when the crust was, let's say, 80 kilometers, after this characteristic time, it would be only 30 kilometers. And for the geologically relevant values, the relation between characteristic time for erosion and the erosion coefficient can be described and is plotted on this diagram. And from different studies, the erosion coefficient can be specified more. And then it's assumed that it is in between 10 to third power and 10 to fifth square meter per year. And using this diagram, we can obtain the characteristic time for the erosion, which would be 10 million to 1 billion year. In the second model, there's only gravitational collapse described. The evolution of thickness is given by such a formula. The characteristic time for gravitational collapse is given in such a form. And again, in previous case, the relation between characteristic time for gravitational collapse and viscosity is plot. For the values of viscosity between 10 to 19 and 10 to 24 Pascal per second, we can see that characteristic time for the gravitational collapse is 10,000 to 1 billion year. Next stage, we can combine the two processes, the erosion and gravitational collapse. And the evolution of thickness is given by such a formula, with characteristic time now for both gravitational collapse, combined gravitational collapse and erosion. In this case, the characteristic time is a function of parameter c, and this c is the dimensionless number, and when it approaches 0, then the characteristic time is equivalent to the characteristic time for the erosion. Whereas when it approaches infinity, then the characteristic time is equivalent to the characteristic time for the gravitational collapse. And finally, we could plot the relation between erosion coefficient and viscosity and define two fields, the one for gravitational collapse and the other for the erosion. And I would like to point to you that already this author mentioned that there is gravitational collapse and erosional collapse. So what are the geological evidences of orogenic collapse? So the first and the most striking evidence for the orogenic collapse is the absence of mountains on the surface and also absence of deep mountain roots. And here I present you other evidence which are considered to be the evidence for the orogenic collapse. And I'll show you an example from Caledonian orogenic belt. The Caledonian orogens was formed due to the collision between Laurentia and Baltica, and in the middle, Silurian to early Devonian. But this collision followed the convergent state when the Iapetus Ocean was consumed under the plate. And due to collision, the Iapetus Ocean was closed. The collision was rather short and lasted 30 million years and was followed by the collapse, which also was assumed to last around 30 million years. And what are the extensional structures in Caledonians that indicate that orogenic collapse could take place? First of all, there are huge detachment zones, above which the sedimentary basin were formed. And it's stated usually that these detachment zones and then the sliding along these detachment zones was formed at the same time as the Devonian basins were formed. In these regions, there are observed exhumations of high-grade rocks, which experience a very fast, large, reaching 10 to 20 kilobars isothermal decompression. And there are also various other extensional structures on the smaller scale. And here I show an example of Bhutans. And in this case, the process responsible for the orogenic collapse is the adduction. And in literature is stated that adduction is responsible for the orogenic collapse. But as I said before, this definition, this process doesn't fit to the definition of the orogenic collapse. To conclude, I would like to ask a question. Is orogenic collapse only driven by the contrast in gravitational potential energy? And what are the role of other processes that can contribute or trigger the orogenic collapse? And how about adduction and erosion? And I think that the process of orogenic collapse is not really well understood, and I could also see it in the literature. There is some debate about what does it mean, and there are people showing various different opinions about it. Thank you.